How precise is precision agriculture? What's at stake with getting this right? Nobody cares more about getting data collection precise than researchers. They're on the cutting edge of using digital tools to characterize and understand soil and agronomy.
We're kind of at the state where we have the tools will work, and now what we're doing is expanding our agronomic understanding of it.
That's Dr. Steve Shirtliffe at the University of Saskatchewan, who pivoted his research career from agronomy to digital ag about 7 years ago. He's joined by his colleague in the Department of Soil Science, Dr. Preston Sorenson, who focuses his work on mapping soil properties.
We have approaches that I'll say academically, we can reliably measure the carbon content in a soil sample with quite a bit of precision, but it does come down to how do you cost effectively do that at scale.
Preston and Steve talk today about digital tools, ag data, artificial intelligence, and what the future might hold for precision agriculture.
I think we're a ways off from really having a ChatGPT of precision ag, but using machine learning to make sense of that data when we find it is just standard procedure.
The future of precision agriculture on today's Future of Agriculture podcast. Well, hello, fellow ag nerd. Thank you so much for joining me for another episode of the Future of Agriculture. My name is Tim Hamrich, and every week you and I get to hear from the farmers, founders, innovators, investors, the people shaping the future of the ag industry. I'm very pleased that this quarter, the Future of Agriculture podcast, is brought to you by our quarterly presenting sponsor, which is SwapMaps. Because when you know more, you grow more. SwapMaps variable rate technology helps you understand the why of field variability and how to better manage it. Understanding soils is the core of a successful fertility program, and SwapMaps allows you to map, measure, and better manage your soils using data that accurately delineates areas with similar fertilizer response characteristics. Turn your data into actionable value with SwapMaps. They're your trusted variable rate provider on millions of acres currently with a 98% retention rate. SwapMaps, they do variable rate right. Learn more at swapmaps.com. Book a consultation or just check out more information. That's swapmaps.com. But you don't have to take just my word for it. Listen to Tyler Kessler talk about how SwapMaps opened his eyes to the potential of variable rate and how it's worked for him as both a farmer and agronomy consultant working in southern Saskatchewan.
I started being introduced into SwapMaps, and that really was the turning point of where I believed it started to make sense for me. I could see it started making sense for the clients. And it was the base layer of if you're actually dealing with physical properties. You're not dealing with just yield maps. You're not dealing with imagery to try and, market a scalable business. In our case, we've got 99% retention. Anyone that has tried it continues to increase their acres and they want more.
That website, once again, is swapmaps.com. And thank you to SwapMaps for supporting Ag Innovation and the Future of Agriculture podcast. All right, back to our featured conversation with two leading researchers that are both thinking deeply about digital tools from slightly different perspectives. I wanted to have a conversation here about cutting-edge digital tools and the future of digital ag, and I definitely think we succeeded in bringing that to you here today. Both Steve and Preston, in my opinion, have some great insights about the best ways to collect and analyze data. They're thinking deeply about variability and how to utilize all of this understanding for real-world outcomes on farms. Dr. Preston Sorenson is a research associate in the Department of Soil Science at the University of Saskatchewan. His work focuses on mapping soil properties using a range of data sources, usually, he says, from satellite imagery and elevation data. He also works a lot with soil sensor systems, in particular for rapid carbon measurements, and carbon is something that we will definitely get into today. Dr. Steve Shirtliffe is a professor also at the University of Saskatchewan, but in the Department of Plant Sciences. As I mentioned in the opener there, he pivoted his career about 7 years ago from his focus in agronomy to now working in the area that we'll broadly refer to as digital agriculture. His focus is on crop imaging and understanding in-field spatial variability and what causes it. But let's dive right into this conversation here on digital tools. I'm going to drop you in where I asked Preston, the soil scientist, to share how he's using digital tools in his work today.
Yeah, so I'd say in terms of speaking very much as a researcher and as a soil scientist, we know soils are a continuous three-dimensional body on the landscape. So if you're going to talk about soil sampling, you're taking point measurements. So just at one particular part in the landscape. And then you need to decide how you're going to extrapolate that data to the landscape. And what these tools let us do is, instead of sort of what I'll say an expert driven, which is both subjective and labor intensive way to do it, we are able to then take this data, use models to explicitly model how a point of value scales across the landscape. And it lets us really see how soil properties are sort of changing at a landscape level. And then we can then relate that to different other parameters, either for a better understanding of what's influencing, say, something like soil carbon, or how those values are influencing things like crop production, or it also lets us then continuously translate those values across the landscape for management applications.
And soil carbon is obviously a big topic right now, given all of what's going on with these carbon programs and sequestration. What are we learning as a result of this type of work, as far as what does kind of contribute to carbon sequestration?
So in terms of from what these tools are helping us do is this is building on other work, of course, in the past, but we're getting a much clearer picture about how carbon is varying across the landscape, and also what is then influencing carbon stocks in the landscape in terms of things like whether your vegetation inputs of carbon are the highest, and seeing where gains are happening in the landscape. So for example, with some work that we've done in southeastern Saskatchewan, using these mapping tools, we've been able to very clearly see that the carbon gains over time that have happened due to no-till agriculture are not uniformly distributed across the landscape. They're preferentially happening in lower slope positions, which are wetter, tend to have more vegetation production, more natural fertility, which then has significant implications if we're thinking about a carbon monitoring program. Because if we're only sampling our mid-slope positions, we're likely under-characterizing the carbon gains that have happened in the landscape. And also, you have to then think about how you sample in terms of having a fair and unbiased assessment, right? Because you could preferentially sample your lower slope positions and say, look at all this carbon we gained, when in reality, your upper slope positions have gained a lot less. And so it's really highlighting the importance of that landscape and slope position based assessments when thinking about carbon across soil landscapes.
Interesting. So does that mean kind of the next step is, instead of just modeling out, we started planting cover crops, we went to no-till, we'd also be modeling out kind of the topography, I guess, more the landscape factors of a field as well?
Yeah, exactly. So we would need to consider both those management practices and how they're interacting with slope position in terms of where then the gains are actually happening in the landscape.
Yeah. And on that note, and Steve, I'm going to ask you a similar question specific to variable rate after this, but for Preston, do you look at sort of the models being used for carbon sequestration today commercially and think like, man, we're not even close to having an accurate number here, and think like, in the grand scheme of things, maybe the best way to answer this is like, where are we now in terms of accurately measuring soil carbon, and what do you think is possible kind of in the next decade?
So I will say that we have approaches that I'll say academically, we can reliably measure the carbon content in a soil sample with quite a bit of precision, but it does come down to how do you cost effectively do that at scale is one of our big challenges. And I'll speak more specifically the Canadian context, but I think one of the challenges with the spectroscopy-based approach, which is kind of the leading candidate when you look at some of the commercial offerings, is that building models are going to work in a wide variety of soil conditions requires huge amounts of soil samples being taken to build what's called a spectral library for the machine learning models to work on. And because machine learning models are so good at there's a real risk that you what's called overfit to the data. So you're really fitting to noise or really specific conditions. And so if you take that model from one location and you apply it somewhere else, it's not going to work well. And so I would say that we still kind of lack consistent standards and protocols. And this is where I see the role of, let's say, public research or government is establishing standardized protocols and sort of building what I'll call like a foundation or knowledge infrastructure in terms of this data that would enable a commercial offering to take that and then much more realistically and easily offer commercial product to generate that data. And the other thing that we'll see is that the holy grail would be to have a field sensor that works really well. The challenge is that you've got the moisture content variation, lighting conditions are more challenging. And so it's much harder to get a consistent signal. And I would say as a first step, probably getting laboratory-based mid-infrared spectroscopy is going to be our lower hanging fruit, that we could still probably cut the cost of data to 20% of what it is now, or even 10% of what it is now with such an offering. And there's been some really exciting work happening at the USDA with the Kellogg Soil Library. And I know one researcher, Rich Ferguson, who I've met, who's leading some of the work there. So the USDA is doing some really exciting work building a mid-infrared soil library and trying to roll that out at different offices for rapid soil testing. And there's been some work in Canada as well. There's Mervyn St. Louis with Agriculture and Agri-Food Canada's leading, building a Canadian prairie soil spectral library right now that can hopefully then be our foundational information for some of these applications to have much more data to build off of.
Yeah, no, and that sounds promising. You know, as far as having, you mentioned the, I don't know if you called them protocols, but sort of having a base layer from the government to sort of guide the approach to carbon measurement. Do you see that happening in the next decade, or are we still a long ways off from that?
If there's sufficient, investment of resources, I can see it happening. I mean, the question is, will there be the funding to do it? I know of some initiatives here in Canada trying to get that funding together. The analogy that I kind of think is a good comparison is I kind of see it like the development of the internet, right? You look at the massive commercial potential of the internet that has exploded, but the internet's origins in DARPA in the 80s. And developing of standardized protocols and communication protocols was necessary, right, for commercial entities to then be able to have a system and platform to build off of. And I personally see, at least from a carbon measurement framework, that similar kind of protocol development is going to be necessary for standardization.
And the soil libraries that you're talking about would be helpful to that end, but they still need kind of a protocol to determine how exactly to use them in the measurement process, right?
Exactly. You need a protocol in terms of here's how you collect the measurement, here's the kind of instrumentation. Not that it has to be one vendor, but the types of instrumentation that needs to be used. Here's the data processing and cleaning techniques. There's a number of steps to ensure that you're getting as much consistency as possible.
Very interesting. Well, Steve, I want to have kind of a similar conversation with you on variable rate agriculture, site specific agronomy, however you want to frame it up. But where are we at today in terms of like commercially using it accurately? Having the data we need to use these tools accurately, and where do you think is possible to go here in the next decade?
I think we're at the beginning of a long journey, and I think historically we saw. It was in the 90s and kind of the early and mid 90s, we saw the first glimmers of interest in the precision ag area, and it kind of died a death back then because of some of the issues that Preston talked about, just in terms of the machinery side of it and in dealing with the data. Nothing dealing with data back then on, the equivalent of, people were working on, 386 and 486 processors and having to pay $1,600 per Landsat scene just to get it. And all that data is freely available. And the machinery can actually talk to everything. So now we're kind of at the state where we have the tools will work. And now what we're doing is expanding our agronomic understanding of it. We started a precision ag certificate here at the University of Saskatchewan, and this is the first year it's running. I'm teaching a couple of courses in it. I've taught for a long time, and so I like to frame it within a very simple model of what we are doing, especially when we're doing variable rate nutrient management within a given field. There's two things that can really vary: the supply of that nutrient how much is in the soil in a chemical form, how much of it will be released through the year or deposited through the year. So that's the supply of it. And then what the farmer actually puts in the ground, what they actually ban as fertilizer or spread as fertilizer. And the other part of it is, what is the potential demand for that nutrient there? So, and that's normally what is the potential biomass production and yield in there. That's what we can really get a good handle on using imagery data or yield maps. But the other side of it, to understand the soil side of it, we need to work with colleagues like Preston here to really understand what is our depth of soil organic matter, our A horizon depth. How does it change across there? What is the concentration of soil organic carbon in there? How much nitrogen is mineralized in a given year is still a big black box. We know that soil with more soil organic matter mineralizes more nitrogen throughout the year, but how much it mineralizes in a given year, as far as I know, I'm no expert in this, but I know talking to people that are experts, they still there's no good test to measure that. So that's one thing that we have to do, but we do know that it varies. And so we're coming a long ways. We can use hydrological models and look at them. We can validate those hydrological models using satellite imagery, because you can see where the water goes. You can tell the difference in a year. You get kind of different patterns. Some years you'll get where you'll have like a quick snow melt. And if it's a dry year, you can see where all the water runs to the little low spots very quickly and sits there and soaks in, and then down the water courses, you can see that. If it's a dry year, if it's a wet year and you get even rains and there's no runoff, you won't have as much spatial variability there as well. So there's a lot that we understand, but there's still a heck of a lot that we're at. We're still at the very infancy. And I think one thing that we're looking at, though, like when I talked about some of the newer stuff of the field scale variability that we're looking at, is this whole idea of quantifying how much of that spatial variability that's temporally stable. So the spatial variability that over the long run is there, how much does that vary within individual fields? And that's what I really want to get a handle on. We just recently got some funding from WGRF. The goal of this one is to build a map of all of Western Canada at a 10-meter pixel level. And we want to be able to assign essentially how much spatial variability is there within each field in Western Canada. And that will become a driver for the adoption of no-till. Obviously, for fields that have very little stable spatial variability, it's not such a big deal. But for fields that have a large amount of spatial variability, it's going to make economic as well as environmental sense to do that. I think we're just at the beginning if we get back to this, and we're just starting down this road.
And when it comes to spatial variability, what is your sense of how much of a sense the average farmer has in each field of like how much spatial variability is out there? Do they have a pretty good idea, or will it be pretty eye-opening to them how much spatial variability is in some of their fields?
I think most farmers have a reasonable idea. People tell it when they're on the combine, right? Because it's, you can tell when you get to a good spot or when you get to a bad spot because your speed of your combine, even without yield maps. But that said, it does depend upon where you are, and it does depend upon the year that the crop is grown. If you get a perfect year, those pink unicorns that come once in a never time, where the rains in June and July fall regularly, and they're not hard rains that run down the hills and wash down the hills, you can end up in many years without very much spatial variability, except, and this gets back to Preston, except what is there because of the soils. If you have spatial variability in your soils, which you almost always do to some degree, that will have an effect even in the best of years, depending upon what the properties are.
Yeah, no, that makes a lot of sense. I want to ask you both about artificial intelligence. 2023, at least in ag tech, seemed to be like a breakout year, for AI. Not to say that it didn't exist before then. Obviously, it's been around a long time, but it sure seems like it's garnering a lot of attention through, these language models like the Chat GPTs and Bards of the world. How are you all using AI in layman's terms, or as close to layman's terms as you can get? How are you using AI, and how are advancements in AI changing your ability to do your work? And Steve, if you want to start, I'd love to hear your perspective.
Okay, well, what Preston does is similar to what we do. We use a lot of machine learning, which is a form of AI. it's just become the de facto way of doing things. It's just how you deal with these really large data sets. They're all machine learning type of procedures. So whether they be random forest, and there's several other different types, but they're essentially just these methods that go through and find patterns in these multi-dimensional, really large data sets. So if you have all these layers of data, it can sort through them. And if you take a human trying to go through and like doing individual correlations, and I suppose you could try to do multiple linear regressions. It's essentially an evolvement of all that. So it's really central, and to be in many senses, I know I don't know. We just think of it as just this is just how you do it. There's some work out there and kind of trying to have generative AI systems that you could ask geographic, ask GIS type of questions too. I know I've seen a smattering of publications out there, so like a chat GPT that you could show me how moisture affects wheat yield in the Canadian prairies, and as it is right now, like I think the issue with trying to do something like that is the data. Even though there are things like the Google Earth engine, the good data sources are often fragmented, and you need a lot of what we call domain knowledge to find and interpret them. People like myself and Preston and the people that work in my lab to be able to understand what data sets you should apply to what problems. So I think we're a ways off from really having a kind of a chat GPT of precision ag, where you could just ask, how much nitrogen should I put on my field this year? That's a long ways away, but using machine learning to make sense of that data when we find it, to understand how those processes work, is just standard procedure.
Yeah, Preston, did you have anything you want to add to that?
Yeah, I'll just add on, echo what Steve was saying. I'd say as much as our data sets are very large compared to historically what would have been in soil science, we're really limited on the number of soil observations. So we might have large amounts of satellite data that we have for covariates, but in terms of training data, so the data for observation, say at this point we had this carbon value, our data sets are tiny compared to stuff that like a large language model would be using, which limits the types of models that we can use. So because our data sets are large, and then there's always inherent noise in the data sets, we have to be careful with the types of machine learning models we use. So I would say for now, some of the really big advancements in AI, generally, we're still not able to take advantage of yet, at least not until we get larger, more comprehensive soil data sets. And really, the other thing I'll say about there's no sort of magic to machine learning. It can only sort of characterize the variability in whatever you're trying to predict based on what you told it was there. So if we don't have measurements of a certain range of characteristics, there's no way for the model to reliably recognize that. So boots on the ground data collection is still a really, really important part of this process that we're not going to be getting away from anytime soon.
Yeah. Just to echo on what Preston says there, this whole, especially soils data, but even in terms of yield mapping, just to get enough, what often remote sensors will call ground truth data. Those are the data sets that are out there. Like satellite imagery is out there, but well, what is it showing us? Sometimes people like to talk about that there's magic spectra that will tell you this from that. And those just don't exist. There is no magic spectra in terms of reflection from a canopy that will tell you the difference between a plant that's dying from insects, or a plant that's dying from disease, or a plant that's just dying from water. You could get at it by looking at a lot of separate factors, but it's not like you can just click a button and tell it. And some of those things are always going to need boots on ground, and others we could start to understand by looking at them in other ways. Bringing time in it as a dimension has been an important factor for us. For example, we're doing work in mapping kochia infestations, and really what distinguishes a kochia infestation from a crop is not how green it is or how much NIR reflects. It's the timing pattern when it does it. Phenology, how it develops. It germinates later and stays greener longer. That's how we distinguish it. There's no magic wavelength or stuff like that. But the key thing is you need this ground. We like to call it ground reference data, because often the ground truth, it isn't always perfectly true, because often when you measure something on the ground, you're subsampling a small area. it may be true for that 1 square meter, or if it's a soil sample, it may be true for that 2-inch sampling tube, but you do need something to tie it to. So that's always the key thing in agriculture is we need on the ground reference data.
And for you all as researchers, do you all have standard formats for collecting that data, and do you all share it with other researchers at other universities? Is there this, secret society of researchers that all have open source data together, or is it kind of like you got to get your own data?
I can jump in there. So at least in the soil science world, we have a lot of established protocols and standards that do exist for laboratory measurements. I mentioned before, we need new protocols for some of these emerging technologies. As much as possible, we do try to share data. In Canada here, we currently have a funding application in to build a national soil library that we want to make as an open source library available to anyone. Our biggest challenge when it comes to accessing historical data sets and sharing data isn't actually sort of researcher willingness, it's privacy concerns. And typically, and we can understand why in terms of privacy risks, that some of the data holders that exist out there where data was collected under certain conditions that were provided to landowners. And so that ends up being the biggest limitation for data sharing. And I'd say one of the biggest obstacles that still exists.
Yeah, so I would say that on the, certainly on crop yield and yield maps, it's still, that is, of course, private data that producers have. So when we do utilize that data, we use it to train a model, but we don't show, Joe farmers' crop yields of what what their yield map was for a specific area, because, that is a privacy. We have multiple projects, and I know Preston does as well. And there's always, you get into a situation, well, we can use this data to train the model in the confines of this project because we have an agreement for data there. And then with another one, we may have an agreement for using this data to train this model. So it does get complicated. So the nice thing, the part that is well in my discipline, and as Preston's as well, is the whole satellite data, the national satellites, those that are by the European Space Agency, the Sentinels. There's a whole range of Sentinel. We use mostly Sentinel-2 data and a bit of Sentinel-1, as well as Landsat from the Americans. Those are extremely well calibrated, and there's different tiers of data calibration. So the level of repeatability of those is quite good. And I know some of the private suppliers of satellite data have actually improved a lot. Initially, they were kind of it was a bit of a wild west. But that said, yield monitors are another story. Yield monitors, they are great data, but often they are messy data to deal with because there are issues of calibration and of when you get multiple combines in the field and they have different calibration levels, when there's certain problems that come into it. So you have to kind of go through and clean the data and try to standardize if there's multiple machines in there. So that's a real difficulty. And I know in talking with precision ag providers, a lot of them just ignore yield map data because it's such a pain to work with. They don't ignore it, I would say, but they view it as just kind of a informal validation layer. And that's one of the things I know that we're working with CropPro is to bring some of that data in there. So what we are doing is essentially using satellite data to help get rid of some of the flaws in the yield data, making a fusion between those two layers to essentially do that. And you can do that on an individual field basis. And then, of course, you can use that yield data, that fused layer to predict yield using satellite data and other ones as we described earlier.
Well, I know as we kind of get ready to wrap up here, I know earlier you said, you both kind of said we're at the very early innings. We're just starting to kind of understand some of this variability and what's possible out here. And similarly, what you were saying with machine learning being the standard way of analyzing data now, variable rate or precision ag is just going to be the standard way we farm, right, in the future. But with that in mind, with that context, I guess a two-part question. Number one is, how do you think precision ag evolves in the coming decade? And number two, what would be your advice to a farmer listening as far as like what they should be doing today to kind of stay on the cutting edge, but not the bleeding edge of where that's headed? And Steve, since you just spoke, we'll go to Preston.
Yeah, so I would say that kind of building on some of the stuff that Steve was talking about and working on, is that we're going to be doing a much better job of identifying where precision ag does and doesn't make sense, because there are landscapes that are a lot less variable and have a lot less than potential. So I think we're going to be in a much better position to really provide that information about, does this make sense for you as a producer to adopt, and really then being able to go on a field by field basis and understand, is enough of their fields, good candidates for precision ag to warrant adoption. And then I think on that, really with my bias about, my soil perspective, is I think we're getting much closer to having really good soil maps that will characterize the variability within the landscape at a scale that is then useful for precision ag. And we really lack the kind of data tools to do that in the past, both from sort of this open source satellite imagery, which I really depend on for my work, but even the huge explosion in machine learning tools means that, I just need to learn R and Python as programming languages, which are much, easier for me as a non-programmer to pick up, as compared to needing to learn more complicated languages that I would have had to in the past, and sort of building functions from scratch. Now I can rely on existing open source code libraries to do that work. And I guess my other sort of advice to producers, as much as I would love all the data to be open and shareable so I can use it for research, I definitely would advise producers to recognize that their data is an asset, that they should think about who else is getting it and for what applications, and making sure that that value isn't just getting extracted by, others in the supply chain.
And Steve?
We Preston and myself are researchers, and we've talked about some of the issues we're dealing with, where there's challenges in precision ag. But I think we have to recognize that a lot of farms aren't even managing their fields individually. The level of soil testing is not that much. So I think we have a long ways to go. We're not going to ever have a perfect system. We're never going to be able to predict the yield perfectly. And without being able to predict the yield perfectly, we won't know what the correct rate of fertilizer is going to be perfectly. But does that mean we should just stop trying, or recognize that we can't do it? What are you going to do then? Just pick a random number? No, you have to make an informed guess about target yields. And we know that we can do better than just managing a field on an individual, or managing a farm on an individual basis, that we're just going to put, 146 pounds of nitrogen across every canola field is going to grow canola on this farm. We know we can do better than that. When we start to get down to, if there's significant variability, we can start to get down the subfield level. So no system is going to be perfect, but any system is going to be better than, in most cases, than doing nothing at all. So I think that's the clear thing here. There are some real benefits to be reaped from efficiencies and from reducing agriculture's impact on the environment. If we look at crop production, our major greenhouse gas contribution is nitrous oxide, and that predominantly comes from when you have low landscape areas in your field that get wet, and you get nitrous oxide emission from denitrification. That's where most of it is going to come from. So this is something that we're at a state now that we can actually start to manage that within a field. And so, I think if farmers have the appropriate incentives to do this, the appropriate rewards to recognize good behavior and not be expected to just do stuff out of the goodness of their heart. Climate change is a societal concern. I think society has to look at ways of reimbursing farmers for good practices that can reduce Canada's contribution there. So in many cases, if there's enough variability, it's a win-win. Is there a perfect system? No. Is any system better than no system? Yes.
Well, I appreciate both of you guys. I know I'm at the time of I asked of you, but I just want to open it for one more ability to either add anything or emphasize anything we talked about, to kind of put a ribbon on this wonderful episode.
I think I'll just kind of build on what Steve was saying. I think there, at least in Canada, have been some understandable concerns about meeting new expectations around fertilizer use and greenhouse gas emissions. And that's one thing that I see is what precision ag is going to be instrumental in help solving, is making sure we're adding nitrogen at the right place, and the right amounts. And, I think, speaking about the incentives piece too, right? These things come with costs to producers, and over the 20th century, we've asked agricultural producers to produce as much food as cheaply as possible, right? And they've risen to the occasion. And I think if now we're asking for these other sort of societal goals to be achieved, we're now getting the place, I think, where the technology is arriving to help us achieve those goals. And then if that's paired with the right incentive structure for producers, then I'm very optimistic about the future for our soils to both achieve these greenhouse gas goals and also maintain food security.
Excellent. Steve, you get the last word.
I'll just put in a plug for the Precision Ag Certificate at the university. I think that's something I've got a lot of hope for what's going to come now, because I think when we were putting this certificate together, my kind of base idea was this old school idea of teaching people who are involved in agriculture how to do practical skills. Like, back in the old days, they taught them about welding and hydraulics and stuff like that. And what happened? Well, a few years later, people were building air seeders in shops and changing the way how land was managed in Saskatchewan, building companies that changed the way how agriculture is done around the world. I'm hoping that we can do the same thing in the digital realm, that we can get, instead of these farm kids and people working in the ag industry welding and doing stuff like that, they're actually out there coding, and they know the system so well and are so young and smart that they are going to start companies and build a big digital ag economy. Further, we already have the start of one here in Saskatchewan. I see it as being a potential for us to build this digital economy to be a global leader, and the way we have in the area of no-till and crop genetics. I'm really excited about the future.
And that certificate program he's referencing is obviously there at the University of Saskatchewan. It's a new program. Steve teaches a couple of courses in it and said this is the very first year that the program will be running. So it's exciting to hear his vision for what that can become. I think it's also worth mentioning here that both Steve and Preston are each actively working on projects with Crop Pro Consulting, which is a division of SWOT Maps. I know Steve mentioned to me that one project that he's working on is looking at yield data and using that to train a machine learning model to be able to model variability within that field. And Preston talked about one project of using historical soil mapping data to try to link knowledge that's been generated in the past, described by soil surveyors, to slope position and try to explain the soil properties that we're most likely to see based on those past descriptions. I thought each of those were sort of interesting projects that were worth mentioning here. And speaking of SWOT Maps, thank you very much to Corey Wellness and the team over at Croptomistic Technology for not only their sponsorship, but their partnership throughout this past quarter. They've definitely gone above and beyond to advance the conversation about what's happening in precision ag, and that includes, of course, today's episode. Last but never least, thank you for your time and your attention. I do not take it lightly. I'll be back next week with another story of ag innovation.